Okay, now I'll introduce the next talk. It's my pleasure to introduce Leonid Sigal. He's an associate professor at UBC, and he's also a CIFAR chair at the Vector Institute and an NSERC chair. His research interests lie in the areas of computer vision, machine learning, and computer graphics, with the emphasis on approaches on multi-modal representation learning, recognition, and understanding analytics. So thanks for coming to the workshop.
Thank you very much. I'll try to get back to the beginning here. Okay, great. So thank you for the organizers for inviting me to give a talk. And I just want to say that I'm really excited for actually physically being in front of people and talking to students and having a physical conference. I have students who are in their third year who haven't been to a physical conference, which I think is really sad. So it's great that we're back. Okay, so what I'm going to talk about today is data efficient learning for granular scene understanding. A lot of work from my group could be sort of characterized in these ways, but I'm going to focus on two specific works that are sort of more central about talking about these topics. But before I talk about what we actually have done, I want to a little bit motivate the second part of the title, which is the granular scene understanding. So why do I care about particularly doing data efficient learning or learning with less labels in this particular domain? And to think about that, essentially, what I want to do is go through the reason why I think we should do data efficient learning in the first place, right? Why are we here in this workshop? So the first one is just pure scientific curiosity, right? So essentially, if we look at models that are successful, deep learning models that we're working with day in and day out, they started to work reasonably well at this rate, but they require a lot of annotated data. And if we look at exactly the amounts of annotated data that they require, it's pretty exhaustive, right? Like if we look at GPT-3, which is a state-of-the-art NLP model, it required 400 billion words. And if you calculate someone reading at about 150 words per minute, which is pretty quick, there's going to be 400 years of continuous reading, right? So this is at least an order of magnitude larger than what a human does. So in terms of comparing these methods to human, clearly we're not quite there yet. And so there is a clear scientific question of, can we actually build algorithms that's going to sort of match that performance? So that's an interesting question, and I'm also interested in this. But to me, this is kind of insufficient, right? There's got to be a task, or there's got to be a problem that we're also trying to solve as computer vision scientists. So the second reason why we want to learn with limited data is that inherent inability to collect large data sets. So for certain problems, we just can't collect data, right? If we look at medical imaging, for example, certain rare tumors, they occur very rarely. They only have 100 or 200 cases every year, right? we're not going to be able to collect a million examples of a particular tumor. And this is a real problem, which I have a colleague that works in medical imaging. He's facing this day in and day out. Right, so that's an important problem to solve. But again, sort of for me personally, I don't work in sort of domains where this is particularly a challenge. So what is the most motivational for me is sort of this third point. And the third point really has to do is, what do we do when we want to scale vision, right? So if we want to scale vision to actually operate and recognize everything in the world and be able to build algorithms that are really scale up in terms of the number of categories, the objects that they detect, understand the world, and so on, we're going to be inadvertently faced with this problem. And to be able to see this, we can just look at different tasks in computer vision. So sort of going from left to right here, you have image classification, detection, instance level segmentation, and going even further, something like a scene graph generation, where you not only grounding objects or finding objects, but also relationships between those objects, right? And so as the granularity of those tasks increases from left to right, essentially, what's also happens is that the cost of annotation increases as well. And there's a nice paper from ECCV 2016, where they actually tried to measure the speed of collecting annotations for these different tasks, or at least some of them. And you can see those numbers at the bottom, basically for image level labels. For images in COCO or similar data sets that we're using, it takes about 20 seconds per image on average. Whereas if we go for segmentations, that's about 12 times as costly, right? So, and if we go to for example, scene graphs, it's going to be even worse, right? So the cost, and the cost is both in terms of time and money and so on. And so I would argue that it's going to be essentially, backing up to the point of the previous speaker, it's going to be infeasible to really collect the data necessary to be able to address the whole plethora of classes and tasks that we want to do, particularly at the granular scale where those labels are very costly to collect. Now, you can go back to me and say, well, wait a minute, Leon, but there are large-scale segmentation data sets and detection data sets, right? We have them now. Okay, so let's look at that. And if we look at that, there's one thing that becomes really apparent, and it's the fact that it's not the number of instances, but the number of categories doesn't scale so well, right? So if we're looking at categorization, for example, ImageNet or Open Images that are two of the larger data sets, then they have sort of annotations for about 20,000 categories of objects, which is pretty good. That's about how many things a human can name. But if we start to look at detection, for COCO, it's 80 categories. Even for Open Images, which is the largest, to my knowledge, data sets out there, there's about 600 categories. And if we go to segmentation, then that drops to about 350. For COCO, it's still 80, right? So now we're kind of at least 2 orders of magnitude lower in terms of categories that's been annotated than for the classification test. And this is what's really motivational to me, is try to figure out how do we actually be able to scale the detection, segmentation, and various other more granular tasks to the scale of what we can do with classification. All right, so I posit that this is sort of an interesting and important problem, and I'm going to tell you about some of the techniques that we're doing to actually be able to solve it. And it is quite challenging, right? So if we want to do things in object detection or segmentation domain, it's quite a bit more challenging than doing it in classification. And this comes from our own personal experience where we try to apply sort of models for few-shot or classification models that don't do so well in detection tasks and other more granular tasks. All right, so that brings me to the first work I was going to talk about today, which is Unified Knowledge Transfer for Any-Shot Object Detection and Segmentation. This was work done jointly by 2 of my PhD students, Siddhesh and Raghav. And it was actually presented at the virtual version of this conference a year ago. Okay, so the setup is what I said, is basically we want to learn effectively detection or segmentation networks using as few labeled images as possible, doing it as a very data efficient manner. So we're not the first ones, of course, to think about this. There are classes of methods that address these types of challenges. One of them is weakly supervised object detection. And in weakly supervised object detection, what you're given is essentially an image level labels, and you're trying to learn detectors, right? So on an onset, this is really good, right? Because that addresses the need to have these bounding box or segmentation annotations. We can just use all of the data in our open images with 20,000 classes. It should all work. Of course, it's very difficult to get these models to actually perform well in terms of the detection tasks or segmentation tasks for that matter. The other paradigm that people have been developing is this few-shot object detection paradigm, where a scenario is a little bit different. You define the base classes and novel classes, and you assume for the base classes, you have lots of instances of bounding box annotations or segmentations. And then and so you can learn good detectors, and then you want to transfer that information somehow to the novel categories that have only few annotated instances. And then there is yet another setting, which is semi-supervised object detection setting, which is essentially an extension of what I just talked about, where in addition to these base categories and novel categories, we also assume image level annotations for both the novel and the base classes. And our algorithm is going to be in the space. And within the space of semi-supervised models, there's 2 variants, what we're going to call zero-shot, which allows you to deal with no annotated object detection instances or segmentations for novel classes, or the few-shot, where you do have a few instances that have been annotated. Okay, so one of the issues with previous methods and these 3 paradigms that I've talked about is that the work in these areas has been largely siloed. And so the types of approaches that you use for each one of those formulations is quite different. And so one of the onset things that we wanted to do is propose a fairly simple unified framework that would be able to scale seamlessly across the different settings and also across the levels of supervision. Right? This is also backing up this claim that we have long tails and we want to be able to deal with sort of different number of instances which might be present for particular classes. Okay, and just as an aside, I want to say that when we were doing this, we were quite doing this alone. Now there has been other work that looks at different forms of supervision that was done either concurrently or actually is at the one on the right is actually at this conference. So I want to go give credit to the work that's been done. It's now termed omni supervision. So that's a very interesting direction that I'm going to come back to a little bit. Okay, so let's talk about our approach. What do we actually do? So our model builds on top of BestStar RCNN, which is a traditional object detection pipeline. That pipeline essentially has two stages. The first stage, given an image, produces a set of proposal bounding boxes that may contain objects. And then the second stage essentially would take the features out of each one of those proposals and classify them whether in fact that proposal contains an object of interest. And if it does, regress the bounding box or regress the segmentation in order to actually ground that object in an image. And so what we're going to do is basically modify the second part, which does this detection and segmentation. And we're going to do this through two stages, which we call base training and fine tuning. I'm going to explain what those things are. But essentially what we're going to do is we're going to learn a mapping from weakly supervised to much stronger, much better, fully supervised detectors for the base classes, because we do have enough annotations to be able to do that. And then we're going to use the mapping to then transfer those mappings into a novel classes that may or may not have any instance level supervision. And we're going to do this using a multi-modal similarity metric that I'm going to discuss in a minute. Okay, so to ground this a little bit, because I'm talking about base, novel, right? These are a little abstract. You can think when I'm talking about base classes, you can think about COCO, right? So any categories that have object instance annotations, have segmentations, that data is fully annotated. And when I'm talking about novel, think about something like ImageNet. So image level labels, but for a large number of classes, let's say, 22,000. Now for actual experiments, we do a little bit less scale than that, but this is the vision. Okay, so what do we do for the base training? For the base training, we do two things. First, we train weakly supervised detectors for both base and novel classes. Remember that we assume that we do have image level supervision so that we can do that for both base and novel classes. And we're going to get our detectors that I'm illustrating using a function f, which is represented using a neural network. Now, the second thing that we do is for the base classes, we also essentially use learn adapters or refiners that refine those weak detections into a very good, strong detection performance, right? So effectively, what we're doing is expressing a proposal classifier as a linear combination of the two terms. The first term is our weakly supervised detector. The second term is our refinement. And you can think of those as producing just logits that you're summing together. Now, this is what happens for a classifier. You can do the same thing for a regressor. The regressor, you start with proposal boxes, right? And then if you have additional data, as we do for base classes, then we can essentially train regressors that would refine those bounding boxes. And we can do the same thing for segmentation as well. I'm just not showing on the slide though to clutter. Now, that's what happens for base classes. What do we do for the novel classes? Remember, for the novel classes, we might not have any instance level data. So for the novel classes, we still have a weak detectors, so we can take those. We have proposals, so that part is okay. But what we need to do is somehow transfer information from our base detectors to our novel classes. And the way we're going to do that is using a linear combination of these refinement networks, where the linear combination is modulated by this function S, which is a function of the features of the proposal itself, which is going to measure a similarity between the base classes and the novel classes. Okay, very simple. It's just a linear combination. So now, given this, we actually are able to do zero shot already, right, for novel classes. We don't need any instance level annotations for them. But we could have cases where for certain classes, we do have additional bounding box annotation or additional segmentations. What do we do with that? Well, then we just add an additional refinement term on top of the first two that I illustrated before. That's going to directly essentially fine tune to those few instances. Okay, so now we've essentially just decomposed our detectors and segmenters. So essentially what we've done is introduced an inductive bias in the form of this decomposition that actually turns out to be fairly effective for what we're doing. Okay, so now the key to this working is essentially similarity. How do we measure the actual similarity between the base classes and the novel classes? We do this using a multi-modal similarity measure where we take a product of two similarities, one which is lingual, that's agnostic to the actual proposal that we're looking at, and the second one is visual, which is actually as a function of the features of the proposal that's being considered. And the similarity is basically of the size number of novel classes by number of base classes, right? That's the overall similarity, but it's going to be different for every proposal box. So in terms of a lingual similarity, we do something very simple. We just do a dot product of glove embeddings. Those are embeddings for the words that define our classes. If we have classes that's made out of multiple words, we just sum up those embeddings. So something very simple. And what you can see here is the similarity between the novel and the base classes, and it looks fairly, fairly intuitive. Airplane, for example, mostly looks like a car in the air, and it looks a little bit like a boat. The horse looks a lot like a dog and a little bit like a sheep, and so on. Right? So now we can take those refinement networks from dog and the sheep and transfer them to be able to refine the horse detections. Now for visual similarity, it's even simpler. What we can do is just take the base classes and evaluate the weak detectors on the proposal themselves. And then we get essentially a vector that tells us how similar that particular proposal is to every one of our base classes. And so for airplane here, it's most similar to bird, a little bit similar to the boat, and for some reason, a bit similar to a person, but not everybody's perfect. Okay, so now given the similarity, what we can do is train this whole thing. We can train it end to end. We can use any weak detection algorithm you choose as long as it's differentiable. We use a particular one, which is OICR, and we train it jointly with standard faster RCNN loss. Okay, so let's look at some results of this. So the first comparison is to previous semi-supervised methods. This is sort of apples to apples comparison to what people have done in the past, and actually LSDA, which is listed here, which is a method out of Berkeley, was really one that motivated us to look at this problem and was inspirational for what we've done. But you can see that despite kind of simplicity of what we're doing, and we're not using any sophisticated similarity metrics and so on, we do quite well and better than previous methods by a few points. We can do this with a few shot scenario where we have 12, 33, 55, 76, 96 labeled examples. And again, sort of across the board, we can see the improvement with the closest state of the art. We can also do comparisons to few shot object detection. And here we actually see that we perform quite a bit better. Now, one not of caution here. So this is not apples to apples comparison, because what we're doing is we're actually assuming that we do have image level labels, whereas the few shot object detections don't assume this, right? But those labels that are readily available, right? We have ImageNet, we have other data sets, are actually giving us a lot of bang for a buck here, right? Our performance is double what the few shot object detections do. And we can do the same thing for segmentation. And again, here we can see quite large improvements. And finally, what we wanted to look at is what if we actually limit the supervision, right? So as I told you before, the previous two comparisons weren't really apples to apples. This one is. So here what we say is well, what if you take how much ever time is spent annotating object detections for the methods mentioned here, and you spend that time basically just doing weakly supervised learning. So for the same time that you can annotate a bounding box, you can get annotate about 7 images with image level labels. And if you do that, then you actually end up doing better, right? So this points to the fact that if you had a limited budget, at least, if you have a fairly small budget, then doing weekly supervised learning is actually better than doing a few-shot learning. And then we also did this a little bit more formally, where we studied sort of how we can compose these different tasks. So we can sort of mix few-shot supervision at bounding box level with image level supervision. And you can see that if you only have few weekly annotated labels, you actually do worse. But if you start to get to 50-50 or more of weekly annotated labels, then you do quite well. Okay, so these are some of the qualitative results. These are all the classes that, this is zero shot actually. So these are all the classes that weren't seen, didn't have any annotated object bounding boxes or segmentations. So it works pretty well. Okay, so in summary, this was the first thing I wanted to talk about, is basically a unified semi-supervised approach that operates at different range of supervisions and also the types of supervision. We have sort of semi-supervised and weekly supervised data. And it's fairly intuitive, where we just use a linear combination using a multi-modal similarity metric of the refinement networks that we learned for base classes to essentially produce our target classifiers. And we also started to scratch the surface on relative importance of image level supervision versus more granular supervision, which I think is an important thing to think about. All right, so I talked about object detection and segmentation, and now how are we doing on time? Oh, okay, good. Good. So now I want to focus on the second project that I wanted to talk about, and this one is on scene graph generation. Right, so this is a more granular task where, again, you want to, it's kind of like object detection. You want to detect all the instances in an image, but also between the instances, you can have relations that tell you whether, what is the relationship of one object to another, essentially. So this was presented at ICCV last year, about 8 months ago, and this was done by Sudesh and Suhail, who are also PhD students in my group, and it's called segmentation grounded scene graph generation. So just to define the task of what we're looking at scene graph generation. So scene graph is a graph-based representation of images that encodes objects in terms of the nodes in a graph and relationships in terms of the edges. So if I illustrate the task for this particular image, what we're trying to do is detect all the objects that are present in here. Those objects are going to get classified. So those are the labels for the objects. And then they're going to be transformed into being nodes of a graph. And then the directed edges in this graph are going to be actual relationships. For example, person is holding the umbrella, person is wearing a hat, person holding lamppost, and so on. Right? So it's a structured representation that we're trying to get out of the image. So prior work did a lot of work in this area, looking at different architectures, loss functions that we can do for this task, and also the long tail distribution, which is something that was discussed in the previous talk. This is really a problem for this domain, where there are a lot of there's a long tail where some of the relationships really don't happen very often, and some of the objects don't happen very often. And so there's been recently, actually, I don't have any citations on this slide, but there has been a lot of recent work on how to balance that and be able to get scene graphs that operate well both on the head and the tail classes. But all of these methods that sort of predated what we're doing made one particular assumption, and that is that the grounding of objects was essentially at the bounding box level. Right, so all the objects were detected essentially with an object detector, and then the relationship were estimated between them, but effectively all the grounding was done at the bounding box level. Now, we posit that it's actually would be much better if we do this at a pixel level, because depending on the aspect ratio of individual objects, there still might be a lot of clutter within the bounding box that would prevent you to actually reason about the relationships effectively. Right, the relationships really focus on the intersection of where the two objects meet or interact with one another. And so being able to essentially get at that information more precisely by having segmentation in MS, we believe would be helpful. And in practice, we do see that that actually, as you will see, gains the performance. Now, the second part of this is that in addition, by rounding to the pixel level, what we can do is improve the segmentation performance itself, because essentially a scene graph is a contextualized representation for the entire image. And so we can take the information, sorry, we can take the information from all the different objects, integrate it, and be able to refine the segmentations that we have. Now, the main challenge here, though, is one of data, which is consequentially is the topic of this workshop. And the reason is that because most of the, or all of the scene graph generation data sets don't actually have segmentations labeled, right? So they have the rich labels for relations, they have bounding boxes, they don't have any segmentations. We could go off and label all of that data, but this would be prohibitively expensive. And it's also going to take a very long time. So instead of doing that, what we try to do is try to see how can we actually use auxiliary data from data sets that do have segmentations in order for us to actually solve this task without having sort of consistent segmentations on the same data set. Okay, so what the contribution of this was that we have a novel framework for pixel level segmentation grounded scene graph prediction, which can be integrated with any scene graph generation method. We actually make no assumptions about what the underlying scene graph generation method is. You can take any state-of-the-art method. We actually illustrated with multiple methods in our paper, and you can add this to it. And we use transfer multi-task learning in order to do that, and in particular, zero-shot transfer for segmentation, which is going to build on the, some of the constructs that I actually already talked about in the first part of my talk. And we'll see that this results in about 12% improvement on the scene graph prediction performance, and also improvements on the segmentation performance as well. Okay, so let's look at the problem setup. So as I mentioned before, we're going to have two data sets. The first data set is what you typically have for a scene graph generation framework. So this is a large set of images with bounding boxes and the scene graphs as annotated here, but notably no segmentations. Now, the second data set that we're going to have is an object detection or segmentation data set, which does have segmentation and bounding boxes for detection, but notably does not have any scene graphs that are annotated for that data set. Okay, so we're going to call that our auxiliary data set. Now, importantly, we make very little assumptions about what those data sets are, right? So you don't have to have the same categories of objects in the two data sets. You don't have to have the same images annotated in two data sets. The overlap between the two could be sort of minimal. And in particular, way we're going to do this is for our auxiliary data set, we're going to use MS COCO again. So that has 80 categories with segmentation. So that's what we have for our auxiliary segmentation data set. And for the scene graph generation, we're going to use Visual Genome, which is a standard data set that you use for that task, which has 150 object classes and about 150 relations. So one thing to note here, right, there might be some classes in common, but clearly there's at least 70 classes in the Visual Genome that were never, can't possibly exist in COCO, because there's only 80 categories there. Okay, so what do we do for a model? So for the model, we build on the standard pipelines for scene graph generation. So standard pipelines for scene graph generation look something like this, where you typically have an object detector. That object detector detects potential objects in an image. From those objects, you extract the object features, and you also extract relational features that are typically pairs of features from the potential objects that are in possible relation. And you do some sort of propagation among those feature representations, usually using like a recurrent neural network, LSTM, transformer, graph neural networks. You take your pick. There's different papers that do different things in this context encoding part. And then eventually you have a scene graph head that would essentially for every node will predict a classification label. That's a label for an object. And for every edge would predict a label for a relation. Right? And then you do typically a cross entropy loss at the end that backpropagates and learns all of these components. And what we're going to do is just slightly augment this to say we're going to do the zero-shot segmentation. We're going to infuse the features of both objects and relations with those segmentation masks. And then eventually at the end, instead of just having a segmentation loss, instead of just having a scene graph loss, we're also going to have a segmentation loss. Now, if you think about our two data sets and you think of them flowing through this diagram, you will notice that only the images from one data set will basically only get one loss. The images from the other data set will get the other loss because they just don't have the annotations to be able to deal with both losses. That would require us to actually have for the same image two different types of supervision. Great. So all of this could be summarized in 5 stages. I'm going to go through them relatively quickly. They're pretty simple. So the first stage, we do what is typically done for these types of models, which is we train an object detector. In this case, we do faster RCNN, which is fairly typical. And so that can generate bounding boxes for all of the objects in our scene graph visual genome dataset. Now, in addition, the same backbone and the same faster RCNN is trained to also do segmentation on our auxiliary dataset, right? So we can just combine those two. And then once we have the segmentations for our auxiliary datasets for our 80 classes in COCO, we can essentially just do a zero transfer to do zero-shot segmentation for the categories in our scene graph detection dataset, which doesn't have any annotation itself. And to do this, we essentially just use the lingual similarity, which is what I talked about before, using glove embeddings again. So we just take the segmentations from COCO and we linearly combine them to get a segmentation for a particular category within the visual genome dataset. Now, once we have these segmentations, we can simply infuse that information into the bounding box representation Z using a simple neural network. I'm not going to go into the details of what that actually does. That's in the paper, but it's a very simple operation where basically we just combine those two sources of information. So that gives us the new object features, which are now infused with the segmentation information. Now, for relational features, in addition to doing what typical scene graph model would do, which is taking the features of the two boxes in question and maybe the union box, what we do is also create a mask that would ground the relationship itself. And a way we do that is by essentially doing a Gaussian smoothing on the two masks of the objects in question and taking a product of those two Gaussian masks. And what that operation actually does is essentially creates a high density region, high likelihood region on the interface between the two objects, which allows us to focus the information sort of where we believe the relationships sort of most actively are acting. And the parameters of the Gaussian smoothing are actually learned as well. So we actually can learn how much to smooth at the same time as we're learning everything else. Okay, so as I said, our approach could be integrated with any scene graph generation method. We've tried it with two, VC3 and Motif, which were at the time kind of the state-of-the-art methods for doing this. So I'm going to show you some results using that. And but in general, you can integrate it with any approach you like, just using the task-specific loss that approach integrates. And so finally, what we also have is a refinement mask, which is going to refine our masks once we do scene graph, essentially propagate the features and do scene graph predictions. And so now we're going to get better masks that are post kind of scene graph that you can think of actually doing this as multiple stages where now these masks could be fed back into the model and so on, but we haven't actually done that. Okay, so let me show you some experiments. This is run in 3 different settings. The first setting is the predicate classification, where we're given an image, bounding boxes, and object labels. All we need to do is predict relations. So this is the simplest of the 3 tasks. The second one is scene graph classification, where we're given images, bounding boxes, but we need to predict both the object labels and relational labels. So it's a little bit more complicated. And the first one is the scene graph detection, which is essentially you're just given an image and you predict the entire graph. And in terms of performance, we use mean recall that's been established as a better metric in this domain to essentially deal with this long tail distributions. for scene graphs, and we also use average precision for segmentation performance. So let me show you a little bit of performance. It is a long, obligatory table that's in all of the vision papers, but let me focus on a couple of things here. First of all, just showing you that we did do this with two different baseline, motif and VC3, and in both cases, just adding this type of segmentation head and this type of information into the network actually improves the performance across all of three tasks quite consistently. We also tried it with different backbone. So in the object detector, again, it's pretty consistent in terms of increases in performance across all three tasks. We can also look at segmentation performance, and this is on COCO using mass, as comparison masked CNN. And you can see that here we also see different improvements for particular tasks. So in particular for the predicate classification, where we are given sort of additional information in terms of bounding boxes and labels, this actually helps the segmentation quite a bit, but also for other tasks, we also perform better. These are some qualitative results that you can see. So on the left is the baseline model, on the right is our results. Notably that you can see that in our case, we actually get segmentations. To my knowledge, this is the first work where we try to attempt to ground things into segmentations or pixel level predictions for scene graph generation tasks. This is another example. You can see that things like cats and various other things do pretty well. And we also do better in terms of scene graph predictions, particularly predicting labels that are better attuned to the content of an image. And this is a result just to show you that the segmentations also do better. So on the left is the baseline, which is effectively masked CNN, and on the right is what happens after we do this with our method after the refinement. Great. So in summary, this is essentially a model agnostic approach for segmentation grounded scene graph generation and prediction. It works with any underlying scene graph methods, including ones that were developed after we actually did this work. There's nothing specific to the scene graph detection method that we're using. And one nice thing about this work that we're also showing that we can simultaneously improve performance in both tasks, both the segmentation and the scene graph prediction. Okay, so that kind of concludes. Do I have a few more minutes? Excellent. All right, excellent. So that concludes what I wanted to talk about in terms of promoting our work out of a group. And what I wanted to do a little bit is to talk about what I think is interesting for the future. What do I think are interesting open problems, and what are we actually looking at, and what you may see in the next year or two coming out of our group, and hopefully not just our group, other groups, because I think these are important problems. So one of these is omni-supervised learning, and this is essentially a focus on effectively learning with all forms of supervision that you have, right? So siloing ourselves into only learning under a particular form of supervision or particular number of examples per supervision is too constrained. I feel like we need to be able to operate in this sort of much more general framework where we just want our models to consume all possible data that's available to them, do this in a way that is most efficient in terms of whatever annotation is available, produce for us detectors, segmenters, seeing, understanding methods, all sorts of things that are as good as possible. And so, the work that I talked about is along these lines. I also mentioned two other works that do this omni-supervised learning. They actually do much better in terms of dealing and focusing on different forms of supervision. In addition to image level supervision, they look at things like scribbles and points and various other forms of supervision that you may imagine having, and combining all of that information in order to be able to learn in this heterogeneous scenarios. Now, the second thing that I think is important, and this hasn't been addressed as much, I feel like, is sample selective learning and inference. Actually, on the inference side, it's been addressed more. And this is kind of an idea where not all data samples are created equal. And so they should be each sample should be sort of treated with care, right? And so in the inference side, there are actually methods that do this that, for example, use dynamic networks that would change the network architecture or change the network weights conditioned on the sample itself. And this is typically done for efficiency reasons, because at inference time, you want to deploy your methods and use as little computation as possible. But what I'm thinking in terms of a future is that we should also be doing this at training time, right? At training time, we also will have annotated instances, and not all of those annotations are going to be equally effective, right? So some images are going to have large objects that are much easier to detect and deal with. Other will have small instances, occluded instances, and so on. And we should be able to sort of carefully tune how we're learning from this data in terms of making most efficient use of that data. And on the same front, if we are sort of if you're buying into this premise of having data samples that are not all equal, then comes the continual learning and active learning, right? Where you actually want to be able to tell what kind of supervision do I want for a sample? Do I even want the supervision for a sample or not, right? What is the most optimal for me in terms of learning a model? And this is something that we're sort of actively looking into and working, but this is very hard, right? This is an entire other field which people are working on. And then finally, the third thing is something that Dima also mentioned, is imbalanced distributions of labels and dealing with this long tail. This is especially problematic for granular tasks because simple strategies for essentially balanced data balancing don't tend to work very well in those scenarios. And so you have to have more sophisticated models in terms of weighing losses or doing various other things to be able to deal with these types of distributions. And there's also a question of what is actually optimal. What do you actually want, right? Do you want all the classes at test time to be sort of equally weighted and the errors to be equally important or not? Okay, so those are the four kind of future things that I think are important, that I think I'm trying to work in my group. I welcome you to work on these topics as well. I think they're super interesting. Now, this is from a perspective of kind of classes of ideas. There's also all sorts of methodologies, right? Weakly supervised learning, semi-supervised learning, self-supervised learning, transfer learning through foundational models, role of generative models, which was talked about in the morning, data augmentations, and so on, right? So all of those things are interesting. For me, all of them are important. All of them play a role. But in the context of these larger kind of questions and ideas that I talked about on the previous slide. Right. So that's all for me. Thank you. And of course, this work is all done by the students. This is actually a pre-COVID picture of the lab. It's a little bit different now. Hopefully we'll have an updated picture soon, but thank you for coming, listening to my talk. If you're ever in Vancouver, which is, I welcome you to visit, please come, visit our lab, give talks, write me emails. Thanks. Any questions?
You have time for 1, 2 questions?
Yeah.
You have to repeat them.
About the first work you showed.
Yes.
So you talked about like two similarity metrics that you use, the Lingual and the visual one.
Yes.
And there's some data sets in which don't really have textual embeddings for the labels of the images. So if you would rate them, like which one is more important, the Lingual or the visual similarity metrics, like what's the weighting?
So I have to, we did have an ablation in the paper. So I'll just repeat the question. The question was, in certain data sets, you don't have class labels. And so you would have to sort of result to only visual similarity, presumably, and which is more important, the visual or the lingual similarity. In our experiments, to my recollection, the lingual similarity was much better, relatively speaking. But of course, if you don't have access to it, then you can't use it. Now, one thing that you can do, even if you don't have kind of semantic labels, you can learn embeddings for non-semantic labels and use the similarity of those embeddings as a proxy for a lingual similarity. So you can do something like this, but we haven't actually done that. Yes.
Actually, my question is about the second half of the presentation. Oh yeah. My question is about the second half of the talk. So I noticed even in general in CGRAPH literature, like the mean average recall is still relatively low as a metric. We're still getting between 10 to 20%. What do you feel is really holding back CGRAPHs from being a lot more, I guess, recalls? Is it the data itself, the visual genome? Is it poor coupling between language and language that we still haven't figured out in CGRAPHs? Thank you.
Yes. Should I repeat this one or? Okay. So the question is, what is holding back the performance on scene graph generation because the performance is relatively low? It's a good question. So I don't have a very specific answer to this, but I feel like one of the challenges of scene graphs in particular, because the metrics are effectively on the triplets, it's subject, predicate, object relations. And so the space of those triplets is much larger than the space of typical object detection labels or the relational labels by themselves. And so in comparison to others' tasks, the data is labeled more sparsely, right? Because the space of the output space is larger. So I think that's a challenge. There also this challenge of imbalance, and that's been very significant in the past couple of papers that have been published on this area. There's a lot of work on how do you properly balance the data in such a way that you actually do sort of well both on head and tail classes, and that actually drives the performance up quite a bit. So we have paper underworks now where we also look at that, and that actually could improve quite significantly the performance if you just focus on the tail classes, but in such a way that you also don't give up on the head classes as well. Yeah.
Yeah, thanks for the great talk. I'm interested in our first work. We're trying to integrate both the language information and the future of real example together for detection. So my first question is, did you use any pre-trained real language model? For example, the cage prediction model. And my second question is that I'm wondering the comparison between the text-based model and the future-based model. I'm wondering, so how many future examples do we need to get the same performance as the text-based model? For example, maybe one shot is better than the text model, or yeah, maybe we need 10 examples. Do you have any ideas about that?
Sure. So let me answer. I'm not sure I quite understood the second question, but let me do the first question first. So the first question was about whether we tried any language vision models in terms of some of these embeddings and other things. And the answer is not yet, but I think if we did, that actually would improve the performance. So I believe that actually would make things better. And we just haven't gotten around to doing that. I think that would improve things. I think the second question had something to do about how many shots we need.
Yeah, I'm wondering the performance comparison between the text-only model and the future-only model. So how many, for example, future examples do we need to get the same performance as the text-only model?
I see. So I can partially answer that with the results that I showed, right? Because there, what we did is we essentially spend our budget weekly annotating the data. So instead of sort of spending one shot to get one bounding box, right? We spend that amount of time essentially just getting image level labels, and we were able to do better in that case. So I think at least to a certain extent, the sort of weakly supervised models or these foundational models or whatever you want to call them, multi-modal models with language and vision would actually do quite well initially, but then eventually you're probably going to need some samples of what the bounding boxes actually are around the object to further refine the performance. That would be my guess. But that's purely a guess at this point because we haven't done any experiments to back that up.